Hello, we are going to talk about 11.6 vectors and equations of planes. So suppose that if we have an x and y axis right here, let's say x, this is y, and this is z, a three-dimensional plane, so that's z, and then let's say we have a plane, let's say that this is the plane. Sometimes we identify that plane as pi, right? And now let's say if we have some point A, let's say we have a point A in the plane and then point B in the plane right there, and there's a vector between them right here, right? So that's the vector AB, right? Then we can draw and if we think of this, the origin right here is point 0. Let's do a different color. Let's do this 0 right here, right? And then if we have let's say we have a vector OA going right here, that's that position vector, right? And then we can think of we need to draw an equation of a plane, or a vector equation of a plane. We need to have two vectors going in two different directions, right? That are in the plane. So if we call this one U right here and this one V, good, then we can write the vector equation of the plane. And the vector equation of the plane would be, if we say R is, that will correspond to every point in this plane, right, is some vector R, right? And we start at our position vector, which would be A, plus, then we could scale both these vectors in any direction, and then we'd be able to get, as long as they're in the plane, and we can scale it, and we'll go alpha, and we're going to go U, vector U, and then some scalar beta times vector V in the plane, and this will represent every every point in the plane. Where vector R, we can let that be some point x, y, z, right? X, y, z, right? And we'll let vector A be a position vector, and we'll call that x1, y1, z1. That will correspond to the exact points there, since that's the position vector. And then after this, we're going to have some scalar alpha, and we'll let U, like we've done before, U1, U2, U3, plus scalar beta, and then V would be V1, V2, V3, right? So if we have two vectors in the plane and we know a point in the plane, then we can draw the vector equation of the plane. And this is the vector equation of a plane. Good. And then we can make the parametric equations, right? The parametric equations, just like we've done before. I can just, I know my x coordinate is going to be x1 plus alpha u1 plus beta v1, and then my y coordinate is going to be y1 plus alpha u2 plus beta v2, right? And then this is the z coordinates will be z1 plus alpha u3 plus beta v3. So these are my parametric equations. And then if I wanted to do Cartesian, then I can go ahead and eliminate the parameters alpha and beta, and then I can end up with a parametric equation. And the parametric equation would end up looking like this: ax plus by plus cz equals some d, right? And this would be my Cartesian. We could try to eliminate it, but we'll just see it in an example. If we want, in our next example, we'll show how we can take, our vector equations and make parametrics, and then eliminate the parameters alpha and beta, and come up with this Cartesian form of a plane. So, and that's what we're going to do next. So, in our example 38, it says given the points A 1 0 1, B negative 1 0, and C 0 1 negative 1, find the equation of plane ABC that these points are on, and we want to find it in vector form, then in parametric form, and then Cartesian form, and then hence show that the vector whose components and coefficients of the Cartesian equation, so the Cartesian equation is normal to the plane, right? So we'll get to that in a sec. So, but first, let's do the first one. It says we want to find a vector equation. We want to find the vector form of the equation, right? So we have these points. I know the points, so I'm going to find two vectors. And the first vectors I'm going to need two vectors in two different situations, in two different directions. So AB would be negative 1 minus 1, so that would be negative 2. And then 1 minus 0 is 1. And then 0 minus 1 is negative 1, so that's AB is in that plane. And then I can find the vector AC, right? And AC would be 0 minus 1, so that's negative 1. And then 1 minus 0 is 1. And then negative 1 minus 1 is negative 2, right? So I got two vectors in the plane, and then I can pick any one of these points, but I'm going to pick A, and I can write my vector equation of the plane. So R is going to go through, I'm going to pick this point 1 0 1 0 1 right here, and then I'm going to have some scalar alpha, and I'll go AB, so it's negative 2 1 negative 1, and then plus some scalar beta, and negative 1 1 2. Good. And so that's my vector equation in vector equation form. Now in parametric form, right, all I would do is if I were to do parametric form, I would know my x coordinate would be this top row right here. So my x equation is going to be 1 minus 2 alpha minus beta. So that's parametric with parameters alpha and beta. And then y, my y coordinate would be 0, and I can write alpha plus beta. And then z is going to be 1 minus alpha minus 2 beta. So that one is my parametric form, right? And now I want to write my Cartesian form. My Cartesian form, I want to eliminate this parameter, right? So if I want to eliminate the parameter, then what I'm going to do is, well, I can easily, if you could see, I can add these two together, right? If I add these two together, what am I going to get? X plus y. I'm going to get x plus y on one side. Then I'm going to have 1. Negative 2 alpha plus alpha is just minus alpha, and these two cancel out, right? But if I go ahead and look at these two, right, what can I do? I want to get rid of, I've already eliminated the beta, so I want another equation, so I'm going to get rid of the beta in this one, and then I can multiply this equation right here by 2, right? And then I'll get 2y plus z, so 2y, and then I'll have a z equals, I'll just end up with 1. Then I'll have 2 alpha minus alpha, so I just have plus alpha, right? And then these two will cancel. And then you can see right here, I can just add these together real quick, and I'll end up eliminate the alpha. So I'll have x plus, when I add the y's, I'll end up with 3y, and then plus z. These alphas will cancel, and I'll get 2. So here is my Cartesian equation to the plane right here. So I've done that one. And then last, it says, hence, show that the vector equation of the components of the coefficients of the Cartesian equation, so the vector of these, the coefficients of this Cartesian equation. What are the coefficients? 1, 3, 1. So they want us to take 1, 3, 1, right? And show that it's normal to the plane. Well, if it's normal to, if that's our vector, right, and it's normal plane, then I can check any of the two vectors that I have here. So, and what happens if I take the dot product? If it's normal, it should be equal to 0. So if I check this one, I'll go -2, 1, -1, right, and do the dot product, and this would be -2, this would be +3, and that would be -1, and that is 0. So therefore it's normal to the plane. And this brings up an important concept about equations of plane, right? The coefficients from my equation to any vector, a Cartesian equation of plane. So when I have something like ax plus by plus cz equals some value d, the vector, right, a, b, c from these coefficients is the normal vector to any plane, right? And so if I have any plane, this normal vector right here that is perpendicular to n, right, that is perpendicular to the plane right here in any direction, just like this, that we know that that coefficient is a, b, c from our Cartesian equation of a plane. Sound good, guys? Thanks.